All right, let's dive right into this explainer. From the arc of a perfectly thrown basketball to the precise curvature of a satellite dish, parabolas are literally everywhere. Today, we're going to learn how to visually construct these quadratic functions and then use those graphs to uncover their exact algebraic solutions.
Here's our blueprint for today. Decoding vertex form, identifying key features, graphing from a table, solving by graphing, tackling the zero misconception, and finishing up with a recap and a transfer task. Section 1. Decoding vertex form. Let's look at the fundamental equation that acts as the genetic code for our parabola. This is vertex form. Y equals A times the quantity x minus h squared plus k. This formula provides us with immediate, explicit instructions on exactly how the graph is going to behave on the coordinate plane. Breaking this down, that a value up front, that dictates if our parabola opens upward or downward, and it also controls the width effect, so whether it's stretched out or compressed. Meanwhile, h and k are crucial. They pinpoint the exact coordinates of the vertex, which is the turning point of the graph, and the axis of symmetry, that's just the vertical line cutting right through the middle, given by the equation x equals h. Section 2, identifying key features. Now that we know what these variables actually mean, let's pull the key features out of a real equation. Pause check number 1. Take a brief moment to look at this equation. Y equals 2 times the quantity x minus 3 squared plus 1. Based on the blueprint we just went over, what are the vertex coordinates and the axis of symmetry? So because our h value inside the parentheses is 3, and our k value on the outside is 1, our turning point is exactly at the coordinate point 3, 1. And because of that, our axis of symmetry has to be the vertical line x equals 3, passing straight down through that vertex. Section 3, graphing from a table. Let's translate these mathematical features into a physical graph. The trick here is knowing how to translate those key features into a perfectly drawn curve using a simple table of values. For the equation y equals the quantity x minus 2 squared minus 4, we want to center our table right on our vertex at x equals 2. From there, we just input surrounding x values, like 1 and 3, or 0 and 4, to calculate our y outputs. Doing this reveals perfect algebraic symmetry on both sides of the vertex. Now let's actually build this graph. First, plot the vertex at 2, negative 4. Next, plot those symmetrical points from our table like 0, 0, and 4, 0. Then, just draw a smooth U-shaped curve right through them. When you look at this completed shape, notice that our domain spans all real numbers from left to right, while our range is strictly restricted to y values greater than or equal to negative 4. Section 4, solving by graphing. Let's see how this visual shape actually solves an algebraic equation for us. Whenever you're asked to solve a quadratic equation that's set to 0, you are quite literally just looking for its x-intercepts. The graphical feature of crossing the horizontal axis is exactly the same thing as finding the algebraic roots or solutions of the equation. Looking back at our plotted graph for the equation 0 equals the quantity x minus 2 squared minus 4, the parabola crosses at x equals 0 and x equals 4. We can flawlessly verify these graphical roots by substituting them back into the original equation. If we plug in 0, 0 minus 2 is negative 2, squared is 4, minus 4 equals 0. If we plug in 4, 4 minus 2 is 2, squared is 4, minus 4 is also 0. It's a perfect match. Section 5, the zero misconception. Before we finish up, we really need to address a major trap that catches a lot of algebra students. Pause check number 2. Think about this visually for a second. Does every single quadratic function have to have 2 distinct real zeros? Basically, does every U-shaped parabola have to cross the x-axis exactly 2 times? The answer is unequivocally false. Quadratics do not always have 2 distinct real zeros. Sure, it can cross the axis twice, but it can also touch the axis just once if its vertex rests exactly on the x-axis. Or it can float entirely above or below the axis, opening away from it. If that happens, there are absolutely 0 real roots. Section 6, a recap and transfer task. Let's lock in what we've learned and give you a final challenge for your own coordinate plane. Vertex form. Y equals A times the quantity x minus h squared plus k clearly reveals the vertex, axis of symmetry, width effect, and direction of a parabola. We can use a table centered on that vertex to plot symmetrical points and sketch a highly accurate graph.
And remember, solving a quadratic equation visually simply means locating its x-intercepts, keeping in mind that there may be 2, 1, or 0 real solutions.
Here is your transfer task. Apply these steps to graph the quadratic function y equals negative the quantity x plus 1 squared plus 4 and estimate its roots on your own paper. Once you've mapped out its key features and found exactly where it crosses the x-axis, ask yourself this. If this parabola represented the exact flight path of a launched rocket, what would those specific roots actually mean for its journey?